minus 5 over 2. Great. Okay, that's cool. But now let's illustrate how it would work if we looked at the other side of the previous theorem. Let's look at the sine areas of the three oriented sides. Let's look at AB first. Okay, so with AB, the oriented triangle OAB, we calculated sine area just by taking the cross product of the vector here times the vector there divided by 2. So those vectors are just the coordinate vectors associated to the points A and B. So this vector here, emanating from the origin to A, will just be the vector 2, 1. And the vector OB will be 1, 4. So the oriented side AB has sine area 1/2 of 2, 1 cross 1, 4. And that's 2 times 4 minus 1 times 1. That's a 7 over 2 altogether. So that's the sine area of the oriented side AB. And what about the oriented side BC? Well, then we have to take the vectors B and C here. So basically the coordinate vectors of these things, which is 1, 4, 3, 3. Okay, the cross product there is 1 times 3 minus 3 times 4. That's minus 9 all over 2. And finally, CA, we have to take these points and their associated coordinate vectors, 3, 3 cross 2, 1. And that's equal to the cross product 3 times 1 minus 3 times 2. That's minus 3 divided by 2. So you can see that we're doing something a little bit different than we were doing here. Here we had to find differences between points. Okay? Here we're just relying on the actual coordinates themselves. But admittedly, we have to do more work. Do 3 of them. Okay, when we add up all of these side areas of the oriented sides, what do we get? We get 7/2 for S of AB, minus 9 over 2 for S of BC, minus 3 over 2 for S of CA, and that totals minus 5 over 2. So we do get the same answer as in the original calculation. So that triangle sine area theorem that we just talked about has an immediate consequence of a famous formula that's usually associated to linear algebra. It's a formula for the area, or in fact the side area of a triangle, in terms of actually the coordinate points. So suppose that we have a triangle. Now we'll change notation a little bit. We'll call it A1, A2, A3, and the points will be general points. So A1 is X1, Y1, A2 is X2, Y2, and A3 is X3, Y3. And we're interested in the side area of the oriented triangle A1, A2, A3. Okay, here's the formula. Its numerator is a little bit complicated. It has these 6 terms. X1, Y2 minus Y1, X2. Well, that's just the cross product of the associated vectors here. X1, Y2 minus Y1, X2. And then the next term is X2, Y3 minus Y2, X3. Well, that's just the cross product of the associated vectors here. X2, Y3 minus Y2, X3. Plus X3, Y1 minus Y3, X1. Well, that's just the cross product of the associated vectors between this one and this one. Namely, X3, Y1 minus Y3, X1. And all that divided by 2. So the proof is immediate from the triangle side area theorem. This is just a restating of that in a special case when we actually know what the 3 points are. And these ingredients here are just the various side areas of the oriented sides of the triangle. So the natural question is, can we now extend this notion of side areas to more general figures? For example, to quadrilaterals, or maybe to more general-oriented n-gons. Here is a quadrilateral, 4 points, A1, A2, A3, A4, and there's a specific order that we're going around this direction here, so it becomes oriented in the same way that an oriented triangle is oriented. And it's represented by this little circle here that sort of represents the orientation, and that's obvious terminology that we could use to represent such an oriented quadrilateral. And the natural question is, can we have a theory of side areas for these things? Can we get sort of corresponding formulas? So let's investigate this question about how we should approach the idea of a sine area of an oriented fourgon, let's say. This one here, A1, A2, A3, A4. And an obvious thing to do is to say, well, why don't we decompose this into triangles, because we know the sine areas for triangles. So let's pick some point B, in this case, in the interior of this quadrilateral. And then we see that by joining B to the 4 points, we get 4 triangles. And the orientation that we're assuming on the original quadrilateral, A1, A2, A3, A4, automatically induces orientations on each of these subtriangles. Okay? Because implicit in this orientation is the fact that this side is oriented this way. But if this side is oriented this way, then that's consistent with an orientation in this direction of this triangle. Similarly, the orientation of this side gives an orientation to this triangle like this. The orientation here gives us an orientation like this. And the orientation here gives us an orientation like this. So each of these subtriangles is actually a oriented triangle, which is good because then we can take its side area. So a logical progression would be that if the side area of the quadrangle is defined, it ought to have the following formula. It ought to be that the side area is the sum of the side areas of the 4 constituent triangles, namely A1, A2B, and A2, A3B, and A3, A4B, and A4, A1B. Okay, so let's investigate what that would mean. Because we know that each one of these oriented triangles can be further reduced into a sum of 3 oriented sides, or sine areas of oriented sides. So for example, A1, A2B, this triangle here, A1, A2B, its sine area is actually the sum of the 3 sine areas of its oriented sides, namely S of A1, A2, S of A2B, and S of B, A1. Similarly, the next one, A2, A3B, is the sum of its 3 signed areas of oriented sides, namely S of A2, A3, plus S of A3B, plus S of B, A2. And then the next one, which is S of A3, A4B, there it is there, it's the sum of, this line here, S of A3, A4, S of A4B, and S of B, A3. And finally, the last ingredient, the triangle A4A1B, its side area is S of A4A1 plus S of A1B plus S of BA4. Okay, so we have these 12 terms altogether. And now we sit back and just have a look at them. And I think you can probably guess what's going to happen. There's going to be cancellation. So this S of A2B, have a look at that one and this one. Here's an S of BA2. These oriented sides are exactly opposite, so they're going to have negative sine areas. The sine area of this plus the sine area of this is going to cancel. This S of BA1 is going to cancel with this S of A1B. Those are going to cancel. The S of A3B is going to cancel with S of BA3, and the S of A4B is going to cancel with the S of BA4. So all of these 8 terms are going to cancel in pairs. And what's left is just these first 4 entries. S of A1A2 plus S of A2A3 plus S of A3A4 plus S of A4A1. So in other words, if we have a notion of signed areas of oriented quadrilaterals, then S of A1, A2, A3, A4 ought to be the sum of the signed areas of its 4 oriented sides. S of A1, A2 plus S of A2, A3 plus S of A3, A4 plus S of A4, A1. That ought to be correct. And notice that at this stage here, the point B has vanished. There's no more reference to the point B. That means that effectively we've discovered a way of pinning down what this quantity actually is. We can then define this thing in terms of the sum of these 4 signed areas of its oriented sides. Okay, very important that we're first proceeding by thinking about what the definition of the signed area of the region in question is. Now, assuming that we know that, we have to pin down what that signed area is, and here we have pinned down a very good potential choice for what the definition of the signed area of a quadrilateral might be. Okay, so that analysis leads us to the following definition. It's a definition of the signed area of an oriented four-gon. Four-gon A1, A2, A3, A4 is an oriented four-gon, or quadrilateral. And the definition is that the signed area is going to be, just as we said, the sum of the signed areas of its 4 oriented sides. S of A1, A2 plus S of A2, A3 plus S of A3, A4 plus S of A4, A1, closing the circle and coming back to where we started. So A1, A2, A3, A4, in this case, orientation in this direction, fine. Then we have these 4 oriented sides, and they are there. Then if we include the origin here, then we have these 4 oriented triangles, each one corresponding to a side, as well as this one here. But this one here will actually have this orientation. And when we add up the signed area of this, plus the signed area of this, plus the signed area of this, plus the signed area of this, then we get what's a reasonable notion for the signed area of the quadrilateral. And so now we can rewrite that in terms of Meister's formula. So Meister was really the first person, I think, to understand this approach to signed areas of triangles and n-gons. And so this is a formula that he wrote in a paper around 1769. And so in the case of the quadrilateral, here we can state it in this way, that if we have 4 points A1, which is x1, y1, A2, which is x2, y2, A3, which is x3, y3, and A4, which is x4, y4, then the signed area of the oriented quadrilateral A1, A2, A3, A4 is given by this expression here. It's 1/2 of x1, y2 minus y1, x2 plus x2, y3 minus y2, x3 plus x3, y4 minus y3, x4 plus x4, y1 minus y4, x1. And each one of these rows is just one of these terms. So this is just S of A1, A2, this is S of A2, A3, this is S of A3, A4, and this is S of A4, A1. With half, of course. So it's a beautiful extension of the triangle formula. So if we just have 3 points, then the triangle formula that we go down with is just analogous to this, but we just go to A1, A2, A3, and then back to A1. And the beauty of this formula is that once you understand it, you can see that this is automatic how to generalize it to more than 4 points. So we can now talk about the signed area of an arbitrary oriented n-gon. And it's exactly the same story. We just cycle through the various oriented sides, starting from the first, going to the end, and then coming back to the first one. So we covered a lot of material today, done a lot of interesting things. We've really established a good framework for understanding area, the subtlety of area, particular signed area in the plane. It's crucial that we work with signed area. And we're going to see a lot more examples of the power of this thinking, both in the course materials that are associated with this lecture, which I hope you're all going through, but also in subsequent lectures to come. So there's a lot to learn. I'm Norman Walliger. Thanks for listening. I'm Norman Walliger, and welcome to Algebraic Calculus. In today's video, we're going to take this concept of signed areas and start connecting it with the curves that are going to be fundamental in our understanding and development of the algebraic calculus. So we're going to meet some simple but very important examples of curves without actually having a completely clear idea of what a curve is, but we may start with some simple examples. And we're especially interested in the kind of configuration that we're going to be seeing right here, where we have a curve, in this case the parabola y equals x squared, that I hope you are all somewhat familiar with, and a triangle on that curve. In other words, we're choosing 3 points on the curve, in this case the point 1, 1, which is A, the point 3, 9, which is B, the point C, which is minus 2, 4. So these 3 points on the curve determine the triangle. And then we can consider the oriented triangle by choosing an orientation. Say A, B, C. That gives us the oriented triangle that we denote by this little circle here with a little arrow in that direction. Okay, so how would we go about calculating the signed area of this oriented triangle? Well, we're going to do that. The signed area of the oriented triangle ABC is the sum of the signed areas of the three oriented sides. S of AB, this oriented side here, S of BC, that oriented side, and S of CA, that oriented side there. And the individual side areas of these things are obtained in a very nice way by just using our cross product formula. So here's the point 1, 1, and here's the point 3, 9. So we're taking the cross product of essentially the vectors 1, 1 and 3, 9. So we're talking about this point and this point here, and the formula is 1 times 9 minus 1 times 3 all over 2. So that was 9 minus 3 over 2. And correspondingly, the oriented side BC is 3, 9, and minus 2, 4. So we take 3 times 4, which is 12, minus 9 times minus 2, which is plus 18 all over 2. And finally, this oriented side here, from minus 2, 4 to 1, 1, we take minus 2 times 1, which is minus 2, minus 4 times 1, which is minus 4, all over 2. And so 9 minus 3 over 2, that's 6 over 2, that's 3. Here we have 30 over 2, which is 15. And here we have minus 6 over 2, which is minus 3, for a grand total of 15. Telling us that the signed area of this triangle is 15. So it's intuitively the same, perhaps, as a parallelogram formed from 3 to 5 that way. On a grid paper, that would be roughly comparable. Okay, so that's a specific example, and it's good to be able to make that type of calculation. But what we want to do today is we want to go up a level and try to look at this kind of problem more generically, more algebraically. So we place the specific numbers that are appearing here with more general algebraic expressions, and that will reveal more structure to us. It's an important idea that we want to be algebraic, so we want to look at a situation and say, what's the algebraic essence of this? So we go from arithmetic to algebra, and that way we get a bigger picture, we get more information. Okay, so this curve y equals x squared that we're starting to have a look at, and curve in quotes here because we have not defined what exactly that means. That's going to be an important issue for us later on. But anyway, this curve, this graph, this physical object has the special property that it's parameterizable. That means that we can get at the points which lie on it in a relatively easy, direct fashion. And we can say that this equation y equals x squared has a parameterization t comma t squared. In other words, points of this form satisfy this equation, and things that satisfy this equation are of this form. So here the parameter is t, which is just the x-coordinate. So we can describe points on the curve by this parameterization. So for example, we can consider 3 points on the curve, a1, which is t1 squared, a2, which is t2 squared, and a3, which is t3 squared, for some unknown or variable numbers, t1, t2, and t3. So here's the picture. Perhaps one possibility, there might be a1, there might be a2, there might be a3. In which case the t1, t2, and t3 values are just the x-coordinates. So if we went down parallel to the y-axis, we would get a value here, that would be t1, go down parallel here, we get a value t2, go down parallel here, we get a value t3. Okay, so now we have this triangle composed of these sort of generic or variable points on the curve, and we can ask for the signed area of a1, a2, a3. So in this case, the orientation would be this way. Okay, so what's that going to be? So now we make the same kind of computation we did in the previous example, but now instead of having numbers, we have these variables, t1, t2, t3. Okay, so what happens? So t1 squared and t2 squared, what's the signed area of the segment that they form? Well, it's t1 times t2 squared minus t1 squared times t2 all over 2. And then going from a2 to a3, it's the same kind of thing. We get t2 times t3 squared minus t2 squared times t3, again over 2. And then finally going from a3 to a1, corresponding to that side, we get t3 times t1 squared minus t3 squared times t1 all over 2. So now we have this nice algebraic expression. You can see there's a common denominator of 2. And then the numerator would be the sum of these 6 terms. And they're all degree 3. And pleasantly, this degree 3 expression is exactly factorizable this way. It's the product of the linear factors t1 minus t2, t2 minus t3, and t3 minus t1. So you can check that by expanding this out and seeing that you're just getting the numerator here. So very pleasant, this algebraic expression that represents the signed area of this thing here is now given to us by this expression here. And the linear factors that appear here in the numerator are very interesting and important because they alert us to the fact that when 2 of these indices or parameters are equal, then the signed area becomes 0. That's very obvious, right? If A2 and A3 become the same point, then our triangle is collapsing to just a segment, and it obviously should have 0 area. Okay, so now let's look at a slightly more sophisticated example, where we go from a quadratic curve to a cubic curve. Let's consider the curve with equation y equals x cubed. Now that has a graph that looks something like this. We set up coordinates like this. So 1, 2, 3 in the x direction, 1, 2, 3, and so on in the y direction. Notice that I'm using a little bit of compressed coordinates in the y direction so that the steep increase of this curve as x gets bigger is captured a little bit better. So what do we see here? We see the point 0, 0. This is the point 1, 1. This is the point 2 cubed, which is 8, 2, 8 somewhere there. And minus 1 there, and maybe minus 2 or minus 8 will be down there somewhere. So those are some points on the cubic. And now let's consider a general triangle formed by 3 points on this cubic curve. And we'll do that by describing the curve parametrically this way. That t comma t cubed is a parameterization for the curve. Any point of this form, no matter what t is, will satisfy the equation because the y coordinate is the x-coordinate cubed. And conversely, if you have a point that satisfies this equation, then it's necessary to form t cubed, because whenever x is more than t, then y has to be the cube of it. So this is a parameterization of the curve, and using that parameterization, we can express three arbitrary points on the curve in terms of the unknown values t1, t2, and t3. So we have a1, which is t1 cubed, a2, which is t2 cubed, and a3, which is t3 cubed. And I've just sort of illustrated it by choosing some three particular points. But these are supposed to be generic, and then we consider the triangle a1, a2, and a3, the oriented triangle formed by these three generic points. And we're interested in the signed area of this thing. And of course, we can compute that now because we just take the sum of the signed areas of the three sides. So a1, a2 has signed area t1, t2 cubed minus t1 cubed, t2, all over 2. And then a2, a3 will be t2, t3 cubed minus t2 cubed times t3. And finally, a3, a1 will be t3 times t1 cubed minus t3 cubed times t1, all over 2. Okay, so now we can take the 2 as a common denominator, and then we again have 6 terms, each one now degree 4. And now you have to kind of stare at this and say, well, is this going to factor? And it will factor, because the same kind of argument that we saw in the quadratic case will be happening here. If one of the pairs of these t values, say t1 and t2, coincide, so if t1 equals t2, it means that 2 of our 3 points are coinciding, and the triangle is collapsing into a degenerate segment, and the area must then necessarily be 0. That's telling us that the factor t1 minus t2 ought to be a factor of the expression that we're getting here. So we expect, just on the grounds of this argument of collapsing of areas when we have collinearity, that the t1 minus t2 factor, the t2 minus t3 factor, and the t3 minus t1 factor, they ought to be factors of this expression. So once we know that, or have an idea about that, then we can verify that that actually is true, that there's an additional linear factor, because the whole thing has to be of degree 4. And the other linear factor turns out, pleasantly, to be just the sum, t1 plus t2 plus t3. We do expect that there's going to be some linear factor there. Actually, maybe it's not that surprising. If it's linear, it should ought to really be sort of symmetric in t1, t2, t3. So at least up to a multiple, we are not surprised by getting that. In any case, it's still a very nice expression, and it's telling us a nice formula for the area of a triangle, oriented triangle, formed by 3 general points on this cubic curve. Now we can extract from that very nice formula a very pleasant and interesting geometrical understanding that tells us when 3 points on the cubic are collinear. So the points t1, t1 cubed, t2, t2 cubed, t3, t3 cubed, on y equals x cubed, on our curve that we're considering, if distinct, they are collinear precisely when t1 plus t2 plus t3 equals 0. Because the collinearity is equivalent to the signed area being 0. And we have a nice factorization of the signed area's numerator. So that's going to be 0 precisely when one of those 4 factors is 0. And if t1, t2, and t3 are distinct, in other words, if we have 3 distinct points, then the first factors, t1 minus t2, t2 minus t3, and t3 minus t1, they're never going to be 0. So it's only going to happen when the 4th factor, t1 plus t2 plus t3 equals 0. So, for example, here in this diagram, we see the points 2, 8, and here's the point minus a half, minus 1/8, and here's the point minus 3 halves, and its cubed minus 27 over 8, somewhere between 3 and 4. So these points on the cubic are in fact collinear because the sum of the parameters, which are just the x-coordinates, 2 plus minus a half plus minus 3 halves, is in fact 0. Okay, so this opens up a very interesting geometrical investigation that turns out to be very rich. The study of collinearity of points on cubic equations more generally. So this turns out to be a very rich subject, and we will be able to say things in this direction as we proceed. But so we already see that this signed area formula for triangles is telling us something that's interesting geometrically, and that's not entirely obvious in the case of the cubic curves. Now let's look at the same kind of question, but with another important curve that's usually called the unit circle, okay, which figures very prominently in calculus. So the unit circle is given by this equation x squared plus y squared equals 1. And there's a familiar graph with the x and y axes, in this case, labeled so that this segment here and this segment here are, to us, visually equal. Otherwise, we would get something that looks more like an ellipse. Okay, so this is a sort of familiar unit circle, x squared plus y squared equals 1, describing that curve. Okay, now we need to touch base with a very important parameterization of this curve. So this curve also has a parameterization, but it's not the cosine theta, sine theta parameterization that you may have studied in high school. You have to let go of that. So here we're going to use the much more important rational parameterization of the unit circle, which I talk a lot about in my videos. It's actually a fundamental kind of understanding of the circle. Okay, so like one of the first things that you really ought to know about the circle is that a typical point on it can be described by these two numbers, 1 minus t squared over 1 plus t squared, and 2t over 1 plus t squared. So that's a point, and all these turns out to be on the unit circle. That's something that the ancient Greeks knew. In fact, the Babylonians knew about it 1,000 years earlier than the Greeks did, at least. So let's denote by this particular point, let's call it E of t. Okay, so we're giving it a name. And you'll see in the worked examples, if you haven't already